Okay, picking up with this problem. We had 0 over 0 initially. We did L'Hopital's rule, remembering to use a product rule in the denominator. Can't ever forget product, quotient rule, chain rule till you're out of calculus. We still came up with 0 over 0. So we're going to try L'Hopital again. So I'm going to pick up from right here. So starting from right here, we've got the limit as x goes to 0 of 1 minus cosine x over x secant x squared, writing it that way, plus tan x. So then doing L'Hopital again. LH doing L'Hopital. Let's do the denominator first because it's going to be a hard one. A product rule there at first. Plane first, derivative second. So I'm doing the secant squared, chain rule. Multiply by that exponent, decrease the exponent by 1, times the derivative of the inside. Derivative secant is secant tangent. So there's the first part of that product rule, plane first or the second, plus plane second, derivative of the first. So all of this was the product rule on x secant x squared. Then the derivative tangent is secant squared. So there's my denominator. In the numerator, derivative of 1 is 0. Derivative of cosine is minus sine, so I get a double negative there. Simplify, 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 simplify. So I'm going to have the limit as x goes to 0. Let's simplify the denominator there. So that's going to be 2 secant squared x tangent x, and then I've got a secant squared and a secant squared there, so plus 2 secant squared x, and on the top sine x. Now I try substitution again, so that's going to be sine of 0 over 2 times secant of 0 squared tangent of 0 plus 2 times secant of 0 squared. And we just see what we got. So sine of 0 is 0. And it is possible. You can get L'Hopital's just a whole bunch of times. Hopefully I haven't been that mean to you. And that's going to be 2 times secant of 0 is 1. So 2 times 1 squared, tangent of 0 is 0. Secant of 0 is 1, so 2 times 1 squared. And so I've got 0 over 2, which is 0, and there's my limit. So the point to this one is that as long as you still have that form 0 over 0, you can keep doing L'Hopital's rule. Now, there are some problems out there in life, and hopefully I didn't assign any of them in the homework, where L'Hopital's rule just doesn't help that much. That you just, each time you take the derivative, either the expressions keep getting horrible and they don't collapse to something that you could work, or the expressions start to be cyclic. Like, the derivative of e to the x is e to the x is e to the x. Taking the derivative of e to the x doesn't change anything. Derivative of sine is cosine. Derivative of cosine is negative sine. And so there are L'Hopital's problems where L'Hopital really doesn't help. And so if you find yourself where things don't seem to be getting better, or the problem doesn't seem to be changing that much as you do L'Hopital's, that might be an indication that L'Hopital's is just not working for this problem. That it's not going to solve every 0 over 0 problem, but it does help a lot of them. But so far we just have 0 over 0. There are other indeterminate forms, and so that's what we'll turn our attention to next. Other indeterminate forms. Infinity over infinity is an indeterminate form. Now, we've already discussed one particular case of infinity over infinity. That was limits at infinity of rational expressions. And I said you could use a shortcut on those guys. And that is still true. That if you have a limit at infinity of a rational expression, meaning x approaches infinity or negative infinity, and a rational expression, meaning polynomial over polynomial, you can use that shortcut to come up with the limit. And some of you also did these, kind of quote unquote the long way. You could divide everybody by the highest power, so you divide everybody in this case by x cubed and work it out. Those ways still work. But now when we have L'Hopital's rule, if you click on view an example, and you really should try to avoid using view an example, it doesn't help you learn. But if you just want a little hint, so you click on it, they're now going to use L'Hopital's rule every single time they can use L'Hopital's rule. There are going to be multiple ways to do a problem. You're never going to see me doing L'Hopital's rules on problems like this where I already have a method that's quick and easy. So just be aware that even though L'Hopital's applies, doesn't mean you have to use it. We have quick and easy ways to do that. We did this problem long ago, factoring and canceling. Just because L'Hopital's rule applies doesn't mean you have to use L'Hopital's rule. And I just wanted to alert you to that when you get to your homework, they're going to use it all the time now, and you don't necessarily have to. Okay, that being said, over here, the graph of y equal natural log of x is shown on the right. We can conclude from the graph that as x goes to infinity, the natural log of x goes to infinity, and as x goes to 0 from the right, the natural log goes to negative infinity. We aren't going to prove those things. We're just going to accept them as facts. There we can see things a little bit better. And so this is the problem we're going to look at. The limit as x goes to infinity of log base 2 of x squared over log base 3 of 5x plus 3. And recall that I did not have you memorize any new calculus formulas for other base logs, that what we did for all other base logs was what we immediately just changed it to natural logs. That we have plenty of calculus formulas for natural logs, so that's what we're going to do. So that's what I'm going to do first. The first thing I'm going to do is rewrite that in terms of natural logs. And so that's going to be the limit as x goes to infinity of natural log of x squared over natural log of 2 over natural log of 5x plus 3 over natural log of 3. Simplify that dude. So that's the natural log of x squared. We'll simplify the dude. We'll take two steps at once here. Properties of logarithms. An exponent just on my argument. That exponent can come down in front, so that's 2 natural log of x over log 2. Then bringing up that bottom fraction, remember it's nothing but division, so invert and multiply. And then a little more simplification. I've got natural log of x over natural log of 5x plus 3. Natural log of 3 is just a number. Natural log of 2 is just a number. Those are multiplied coefficients. They can come on outside. And so there's the problem we're really looking at. And right here, my form here is infinity over infinity. So I got it all simplified to things that look familiar. But my form is infinity over infinity. And that's what I say down here. The above limit has the form infinity over infinity. Limits of the inform, infinity over infinity, including any plus or minus variation, are indeterminate. For these limits, you may also use L'Hopital's rule. The reason why it's presented in two parts is if we are a proof-oriented class, we would prove it once for 0 over 0. We'd prove it again for infinity over infinity. We're not going to do that. But it's the form infinity over infinity, so I can use L'Hopital's rule. And on the next page, we're asked to do that. So now we've done all the simplification, so I'm not going to do it again. And so that's 2 natural log of 3 over natural log of 2 times the limit as x goes to infinity of natural log of x over natural log of 5x plus 3. We already know that it's infinity over infinity. So we can go to the L'Hopital's. So LH, derivative of the numerator, 1 over the argument. Derivative of the denominator, 1 over the argument. Derivative of the argument, and simplify. Always simplify after you use L'Hopital's rule. Showing every step I can think of to simplify. And what? That's going to be 2 natural log of 3 over natural log of 2. Limit as x goes to infinity of 1 over x times 5x plus 3 over 5. Bring that up and flip it. Which gives me 2 natural log of 3 over natural log of 2. Limit as x goes to infinity of 5x plus 3 over 5x. And here's what I was kind of alluding to, that if you were sitting at the computer and you had no clue what to do, so you were working through view and example, they would use L'Hopital's again here. This is still infinity over infinity. You could use L'Hopital's again, but you can also just use our shortcuts here. Shortcut, the degree of the numerator equals the degree of the denominator. And so I've got 2 natural log of 3 over natural log of 2 times 5 over 5. And so my answer is 2 natural log of 3 over natural log of 2. And that's what I want for the answer. You certainly don't give me whatever decimal that is. Now, if it made you happy to say this, that you could use that 2 as an exponent of 3, that would make, you could do that if you want. I don't care at all. You could do that, but don't tell me what decimal it is. And it wouldn't surprise me if this is what the computer gave, because this is a slightly prettier answer than that one. But there is no more simplification than you can do here. There's no simplification here. Someone out there in the world's going to tell me that that's 9 halves, and I would just take away all the points. You can't cancel the LNs. And so there's that answer. And we'll conclude this video with this problem.